a 200 millihenry pure inductor and a 5 microfarad pure capacitor are connected one by one across a sinusoidal AC voltage source. Sinusoidal AC voltage source. So this time they have not given. This time they are not. They have not given us ERMS. They have given us the complete equation of the voltage. So what is given in this question? L is 200 millihenry 200. What is the meaning of milli means 10 to the power minus 3. 200 into 10 to the power minus 3 henry. So this is 200 upon 1000. We will cut two zeros by two zeros, and 2 upon 10 is 0.2 henry. This is inductance. This is the value of L, and a 5 microfarad capacitor. The value of capacitor is 5 microfarad. Micro means 10 to the power minus 6. So 5 into 10 to the power minus 6 farad. This is the value of capacitor. They are connected one by one across a sinusoidal AC voltage. So they are connected one by one across a sinusoidal AC voltage. And the AC voltage is given as V is equal to 70.7 into sine 1000 t. 70.7 into sine 1000 t. Obtain the expression for the current in each case. Okay, so what is this? This one is the peak value of, it is E naught. Here they have not given EMF. They have given voltage. So we can take it V naught. Also. V naught. Now, case first. When inductor was connected. So we can write it when inductor was connected. So it is given like this. 70.7. It is given like this. So we can write it like this also. E is equal to E naught sine omega t. It implies that E is equal to V. If we compare it, E is equal to V, E naught is equal to 70.7 volts, and omega is equal to 1000. Omega is equal to 1000 radian per second. What is the unit of omega? It is radian per second. So is that clear to you? Is this clear to you? Tell me.
Yes.
Okay. Now, what they are asking, just look. So when inductor was connected, then the circuit will look like this. This is inductor, and this is an alternating current AC voltage source. So E is equal to E naught sine omega t. E is equal to E naught sine omega t. Okay, and the value of L is 0.2 Henry. L is equal to 0.2 Henry. Therefore, XL is equal to omega L. We know that the value of inductive reactance XL is equal to omega L. What is omega? Omega is 1000. Omega is 1000. And what is L? L is 0.2. 0.2. If we take out decimal, 10 will come here and 0 will cancel out this 0. So it will become 2 into 100, that is 200 ohms. So XL is now 200 ohms. XL is now 200 ohms. Now what will happen? XL is equal to 200 ohm. Therefore, so I naught is equal to E naught upon XL. E naught upon XL. If you face any problem in this question, then please tell me. Okay, what is E naught? E naught is 70.7, 70.7, and XL is 200. Okay, if we remove the decimal, it's 2000, and 2 ones are 2, 1000, 2 threes are 6, 7 minus 6 is 1, 1 0 10, 2 fives are 10, now 2 threes are 6, 353.5. If we remove these three zeros, then it will become 0.3535. So we can write it 0.35 ampere. Approximately, I can write it 0.35 ampere. Is that clear to you? I naught.
No.
And in an inductive circuit, I know that current lags behind the voltage, current lags behind the EMF by pi by 2. Therefore, equation of current will be, they are asking obtain the expression for the current in each case. Therefore, expression for current will be I is equal to I naught sine omega t minus pi by 2. I is equal to, what is I naught? I naught is 0.35. 0.35 sine omega t. What is omega? Omega is 1000. Sine 1000 t. Sine 1000 t minus pi by 2. Okay. Now, case second. When capacitor was connected, this is capacitance. So what is the value of capacitance? C is 5 into 10 to the power minus 6. 5 into 10 to the power minus 6 farad. And what is this? This is E is equal to E naught sine omega t. So in this case, we have to calculate XC. What is XC? Value of XC is 1 upon omega C. Okay, 1 upon, what is omega? Omega is 1000. Omega is 1000. What is C? C is 5 into 10 to the power minus 6. Now, 1 upon 5 into 1000 means 10 to the power 3. So 10 to the power 3 minus 6 is equal to 1 upon 5 multiplied by 10 to the power minus 3. If we take it 10 to the power minus 3 to the numerator, it will become 10 to the power 3 upon 5. So we will get 1000 upon 5. So 5 twos are. We can write it like this also. 10 to the power minus 3, when it goes to the numerator, it becomes 1000 upon 5. 5 twos are 200. So 200 ohms. is what? XC. XC is 200 ohms. Is that clear to you till now? Is this clear?
Yes.
Okay then.
So,
Yes. Yes, tell me.
nothing.
Huh?
Nothing.
Okay. Okay. Now, XC is equal to 200 ohm. Now, let's move on to the next slide. So, in this case, I naught is equal to I naught is equal to E naught upon XC. What is E naught here? E naught is this one 70.7, 70.7, and XC is 200. XC is 200. So 70.7 upon 200. So this is the same as we observed in the case of inductance. Inductance also we have calculated this XL, and XL came out to be 200 ohms. And in the case of capacitance, XC came out to be 200 ohms. So 70.7 upon 200 will deliver the same result, 0.35 ampere. 0.35 ampere. Therefore, expression for expression for current will be I is equal to I naught sine omega t plus pi by 2. I is equal to 0.35 sine, what is omega? Omega is 1000 t plus pi by 2. What is why I have written plus pi by 2? Because in the case of capacitor, current always leads ahead of voltage by 90 degree, by pi by 2. So is this clear to you? Is that question clear to you?
Yes, sir.
Okay. Now let's move on to the next topic. Next topic is this one. Next topic is series LCR circuit. LCR. L means inductor, C means capacitor, and R means resistance. So LCR circuit, this inductance, capacitance, and resistance, all these three components can be connected in any way. They can be connected. They can be connected in parallel. They can be connected in series. But we have only series in our syllabus. So let's do it. Series LCR circuit. So how this circuit is drawn? It is like this. First of all, we have resistance, then we have inductance, and after that we have capacitance. All these components are connected in series with each other. After that, here we have EMF. EMF E is equal to E naught sine omega t. E is equal to E naught sine omega t. Okay, and in series there is one important thing in series. When any voltage source delivers a current and all the components are connected in series, then in series current remains same. Current remains same means if this voltage source is delivering current I, then current will remain same across R, across L, and across C. It means that current in R will also be like this, current in L will also be like this, and current in C will also be like this. Okay, so all three of them will have the same current. So what I'm going to do here is current will remain the same in series circuit. So you write it, since current remains same in all components, current remains same in all components in a series circuit, and voltage divides. So current जो है, current in series circuit, current remains same in series circuit. So current will be like this. Current will go. This current will go in R also, in L also, and C also. Current will not get divided, but voltage will get divided. So voltage across this R, we will take that voltage as VR. VR, voltage across resistance, and direction of this current and VR, it is same, because in resistance, in resistive circuit, I have seen that current and voltage, they are in same phase with each other. In a resistive circuit, current and voltage are in same phase with each other. But in an inductive circuit, in case of inductor, I have seen that current lags behind the voltage by 90 degree. Current lags behind the voltage by 90 degree means, if I take current like this, if I take current like this, because I have to take current, the current will remain the same in all the components. That's why I have taken current rightwards. So I will take rightward current like this. So current is like this, and voltage will be like this. Voltage VL will be like this. Voltage across inductance is termed as VL. So current lags behind by 90 degree. That's why I have drawn it like this. Is that clear to you? Is this clear to you?
Yes, sir.
Okay. Now, in the next component, capacitance. So in capacitance also, the current will remain the same. So now I will draw current like this here, and current leads ahead of voltage. So I will draw voltage behind current like this, 90 degree behind it. So this voltage across capacitance will be VC. Voltage across capacitance will be VC. So this circuit diagram is as per the concept of resistance, inductance, and capacitance, which we know. All right. So in the case of resistance, current and voltage are in same phase, so both their directions are same. In the case of inductance, current lags behind the voltage. That's why VL is marked like this, and I is 90 degree behind VL. In the case of capacitance, current leads ahead of voltage by 90 degree. That's why VC is downwards and I is onto the towards right 90 degree. All right. Now, voltage across this VR is equal to IR. Clearly, voltage across resistance VR is equal to IR. Voltage across inductance VL is equal to IXL, and voltage across capacitance VC VC is equal to IXC. VC is equal to IXC. Let I be the current in the series circuit at any instant, then VR is equal to IR. Notes are handy with you.
Yes.
Okay. VR is equal to IR is the voltage across the resistance R, which is in phase with capital I. Its amplitude is first VR vector like this. So amplitude is V naught. Amplitude means maximum value, peak value of voltage. So V naught R is equal to I naught into R. Actually, voltage is equal to current into resistance. Na? That's why V naught R. This is the maximum value of voltage across the resistance. It is I naught into R. Secondly, if I talk about inductance, then VL, and I am marking this vector sign because current is going in the rightward direction, but direction of voltage is changing. That's why I am writing VL vector. So VL vector is equal to I vector into XL, and again the maximum value of voltage, the peak value of voltage across inductance V naught L, it will be equal to I naught XL. I naught XL. Now on page number 19 of your notes, yeah, third point is about voltage across capacitance C. VC vector. VC vector is I vector XC. I vector XC. And again, the maximum voltage, the peak value of voltage across capacitance V naught C is equal to I naught XC. Now, I will draw the phasor diagram as it is seen, as it is drawn on page number 19 of your notes. I will draw the phasor diagram here. So you have to learn how to draw this phasor diagram, because RLC series circuit, RLC, we can call it RLC, we can call it RCL or LCR, same thing. In series, if we if we interchange the positions of these components, then it doesn't make any difference. All right. So this circuit is very much important. It is directly asked in the examination. So phasor diagram, it's better if you learn the phasor diagram of this circuit. Okay, I am going to draw it here, and it is very simple. You will understand it. If you face any problem, then tell me. So in phasor diagram, on horizontal axis we take x-axis, and vertically we take y-axis. So in this case, we will take E here. Always we take the EMF E in the first quadrant of this rectangular plane. So E will be here like this. So what is E? Actually EMF. This EMF is getting divided into three parts: VR, VL and VC. But VR, VL and VC, they all are not in the same straight direction. They all are in different directions. So when three terms, when this EMF E is divided into VR, VL and VC, current is going to be the same. Current is going to be the same, and its direction is also same, but direction of voltage is changing. So whenever voltage divides, then that voltage is always equal to this EMF E. So now first of all I will mark this voltage VR, then VL, then VC. So what is VR? Because current is always a little bit less than EMF. Current is always a little bit less than EMF. So first of all, I will mark VR anywhere in this graph. So I will mark it here. I will mark it here. This is VR, voltage across resistance. This is VR. And in case of resistance, voltage and current, they are in same phase with each other. But we know that current is always a little bit less than the voltage in case of resistance, inductance, or capacitance, anything. Current is always a little bit less than the voltage. So VR and I, they both are in same phase with each other. So let's mark I here. I is here. All right. Now, VR is in this direction and VL is in this direction. Means VL is 90 degree ahead of VR. VL is 90 degree ahead of VR. So let's mark it here. This is VR and VL will be 90 degree ahead of VR. So this is VL. This is VL. Okay. Is that clear to you, Anusha? Why I have taken VL here and VR here? VR I can take anywhere. VR is here and VR and I, they both are in same phase with each other. That's why I have taken I a little bit less than VR. Current is always less than the voltage. So I have taken it a little bit less than VR. And VR is in this horizontal direction and VL is in vertical direction like this, positive vertical direction. So VL is 90 degree more than VR. Is this clear to you? Sure?
Can I ask you,
Hi.
can we end the class after at like 45 because like I'm not feeling well today. Is it okay if we like end at only 45?
Sorry, Anusha, I'm not able to understand. Can you please repeat?
I'm not feeling well today. Is it okay if we like end after 45 minutes total class?
No problem. No problem, Anusha.
Sorry, sir.
No problem. No problem. I just want to finish this portion.
Yeah, no problem. I can finish.
No problem. So I think we have 15 to 20 minutes we have. Are you comfortable?
Okay, sir.
Just give me 10 more minutes. I am going to finish this class after 10 minutes. Okay?
Okay, sir.
Okay. So VL is 90 degree ahead of VR, and in the same way, now VR is in this direction and VC is in this direction. So VC is 90 degree downwards as compared to VR. So VR is here, so VC will be 90 degree downwards. So let's mark a 90 degree angle here. This one, it means that angle between VR and VL is 90 degree. And let's write like this. So here there are two cases. First case is that VL is a little bit greater than VC. So you can see that I have taken the length of VL more than VC. So we can write here like this. VL is greater than VC. I have taken this. VL is greater than VC. Now we have three vectors. One vector is VR, another is VL, another is VC. And the resultant means addition of these three vectors will be equal to this EMF E. Resultant means addition of these three vectors. So first of all, I am going to add this VL and VC. So VL and VC, they both are oppositely directed. VL is in this direction and VC is in this direction. So when two opposite direction vectors are being added, then actually we subtract them. So VL minus VC will be like this. All right. the difference between this length VL and this length VC will be this much. So I'm going to write it like this: VL minus VC. VL minus VC. I'm going to write it like this. Okay, and then I'm going to add. So this one VL and VC, actually we add it, but they are oppositely directed. That's why I have subtracted it. So VL minus VC is the resultant of VL and VC. Now this VL minus VC will get added to VR. I want to add VR, VL and VC, and this total should be equal to E. So vectorically we are adding. So I am going to add this VR and VL minus VC. So this is VL minus VC. Now we add it vectorically. So vectorically we are following the parallelogram law of vector addition. So like this, join it like this, and join it like this. So VR, the resultant, the addition of VR and VL minus VC will be equal to E. Is this clear?
Yes.
Okay. Okay. This phasor diagram is very much important, so you have to learn it. And the current is a little bit behind. The current is little bit behind this E. So what is the angle between current and EMF? It is phi. This time it is phi. This time it is not pi by 2 ahead or pi by 2 lagging behind. It is phi only. So using Pythagoras theorem, we are on page number 19 of the notes. Using Pythagoras theorem, we get E naught square is equal to. Now, this is very much important. Please try to understand. Uh, Using Pythagoras theorem, actually the angle is this 90 degree. And what is this? This is VR. And what is this? This is actually VL minus VC. So I can write like this: VL minus VC. All right. So Pythagoras theorem, in Pythagoras theorem, Pythagoras theorem is not applied to vectors. Actually, Pythagoras theorem is applied to a right triangle. So in this right triangle, what is this length indicates? This length indicates the peak value of VR, and peak value of VR is this one, V naught R. So I will write base square means V naught R square plus perpendicular square. Perpendicular square means perpendicular square means VL minus VC square. Perpendicular square means VL means V naught L minus VC means V naught C. V naught L minus V naught C square. Okay, is this clear? Shall we move further?
Yes.
Okay, V naught R. What is V naught R? V naught R is I naught R. So it is I naught square R square. V naught L. V naught L is I naught XL. I naught XL minus I naught XC whole square. So E naught square is equal to I naught square R square plus, if I take I naught common, I naught into XL minus XC's whole square. Okay, is that clear to you till now? Shall I move on to the next slide?
Yes.
Okay. So E naught square is equal to E naught square is equal to I naught square R square plus. If I take this I naught common out of this bracket, then I naught is I naught square actually. So I naught square into, I can write it like this, I naught square into XL minus XC's whole square. XL minus XC's whole square. E naught square is equal to I naught square in the bracket R square plus XL minus XC whole square. R square plus XL minus XC whole square. But my purpose, my target is to calculate this I naught. So I naught is equal to, I naught square is equal to E naught square upon R square plus XL minus XC whole square. So I naught is equal to E naught upon under root R square plus XL minus XC whole square. I naught is equal to E naught upon under root R square plus XL minus XC whole square. So clearly, what is this? This is current. What is this? This is voltage. And what is this? Actually, this is behaving like resistance. This is behaving like resistance. So let's write it clearly. Under root R square plus XL minus XC's whole square is the effective resistance of this circuit. Effective resistance of this circuit, which is called impedance. Which is called impedance, represented by Z. Z is equal to under root R square plus XL minus XC's whole square. Z is equal to under root R square plus XL minus XC whole square. And this is R square, and what is XL? XL is omega L and XC is 1 upon omega C's whole square. Okay, Anusha, do till here. Just do till here, and tomorrow before the class you have to revise all the things till here. Then I will do some special cases and resonance tomorrow. Okay.
Yes.
Okay, Anusha.